about the test? On the 6th? Yes. Yeah, it's on May 6th. Does anyone know what time it's at? 11:30?
I think it's at 11:30 to 2:30.
Yes, I know. So let's chat about whatever you want to talk about. Basically, the topics are Hamilton circuits. The topics are basically Euler circuits, Hamilton circuits, and spanning trees, and that's about it. It will not cover old topics, so it's everything since exam 2. When I say Euler circuits, that includes also the minimum duplication circuits and also Euler paths and minimum duplication paths. So what do you want to discuss? We can do examples about anything. Anything you want to talk about? Anything or nothing? Yes?
Can you just do like the first diagram in each of these? Just
Sure. Yeah, so this big sort of chart that you see on the second page, is that what you meant?
Yeah.
Yeah, you're meant to look at these as columns. So find an Euler circuit in each of those graphs, and then find a Euler path in each of those graphs, etc. You want to just try one of each? Yeah. All right. How about I will invent another graph and do one of each of these things, just so that I don't ruin the ones on the paper. The ones on the paper, I made them kind of small. You might want to copy them onto your own paper just when you're doing them. All right, let's invent another example. I'm going to try to make it interesting enough so that we can answer sort of all these different questions about it. How about that? And then maybe one of these. Yeah, let's leave it at that. I don't know how this is going to go, but we'll try it out. All right, so let's say this is our graph, and I'm just going to try all 6 of those different things. And in each case, the question, if you look at the questions, in each case the question is either find one of these things or show that it's impossible. So that certainly may be the case for many of these different things. So the first thing is Euler circuit. Hold on, I'm going to save a copy of this. Okay, Euler circuit. Remember an Euler circuit, anybody remember? How do you tell if an Euler circuit exists or not? This is the easy one, if you remember. Euler circuit is the one which uses every edge once without any repeats. How do you know if that exists or not? I know it's been a while.
They're all even degrees.
Yeah, all the degrees have to be even. So I think actually that's not true in this example. All the degrees, all the degs must be even. And in this case, I can see several odds. I got 6 in the middle, 4 over here. You should be immediately focused on the degrees. And in this case, there are many odds. So no Euler circuit is my conclusion. All right, so that was easy, I guess. If you just make up a graph at random, it's probably not going to have an Euler circuit, just because it probably will have some odd degrees. All right, what about Euler path? Anybody remember what that's about?
Only 2 specific degrees have to be odd.
Right. To find an Euler path, you need 2 odd degrees and all the rest even. So for Euler path, this one needs 2 odds and all other degrees even. And that is going to be impossible also. You saw that we had more than 2 odds in this case. So I suppose this example isn't terribly interesting so far. This is also not possible in this example because we have many odd vertices, odd degree vertices. All right, let's try. The next thing is minimum duplication circuit. All right, this one will be interesting. A minimum duplication circuit always exists, so there is no situation in which you should say no, there is no minimum duplication circuit. So a minimum duplication circuit, that is like an Euler circuit, but you are trying to cover every edge with as few duplicates as possible. And again, you should start by figuring out the degrees, which I did before. 3 here, 3, 4, 4, 3. All right, and if they were all even, then I wouldn't need to make any duplications at all. The reason that duplications are necessary is because there are some odds here. And I don't know if you recall, it was a while ago that we did this, but the way to figure out which of those edges do I want to duplicate is you focus on the odd ones and you try to connect them up by duplicating some of the existing edges. So for instance, I'm going to take these two 3s together and duplicate that edge which goes in between them. The reason you want to do that is because since I duplicated that edge, this which used to have 3 edges now has 4 edges at it, and this one also used to have 3 but now has 4. So now I've turned these odds into evens basically by duplicating that edge. I will also say duplicate this edge. There are several ways you can do this, so my way is not necessarily the only way. I duplicate this edge to fix up those two 3s. And sometimes, unfortunately, you have 2 that are not next to each other. Anyone remember what to do in that case? I have 2 edges which are not next to each other. I still want to sort of join them up.
Did you just go to the 2 and then go around to the 3?
Yes, you may be tempted to add a new diagonal edge here, but that is not allowed. It's because what I'm doing here is meant to represent duplications of original edges. And so you have to duplicate sort of 2 edges going from one to the other. All right? It looks like I'm going to end up duplicating 4 edges here. 4 edge dupes are required. All right? And in particular, like those are the ones that I'm going to duplicate in my circuit. All right? Now, this is not your final answer. Your final answer is actually drawing the circuit, which actually covers every edge here and duplicates those 4 edges without repeating any others. So I'm going to try and do that. I'll just do the picture again here. Can you see it all at once? So I'm going to try to make a circuit in here which covers every edge and duplicates these 4 edges over here. And there are many ways you can draw that circuit. But the basic idea, remember, is you want to avoid crossing over a bridge among the unused edges. I know this is a long time ago that we did this, but the idea is I'm going to try and hold in my mind where are all the edges which I didn't go yet, and they all have to remain connected. You want them all to be in the same batch, and you don't want to ever cross a bridge which would separate all of the unused edges. So I'm going to start and end at this vertex here, and I will just start going maybe like this. I'll come down here. Let's go around this way. I'm going to come back here and down, duplicating that edge one first time. All right? I feel pretty good about this so far because where are all the edges I didn't use yet? They're all kind of in one blob over here. You don't want to divide the unused edges into 2 separate areas because then it's impossible to cover both of them. But all the unused edges at this point are in sort of one big continuous zone. All right, let's just continue then. So I'm gonna go, let's go down here, across the bottom here maybe. Maybe I'll go around this corner and then come immediately back. Remember, I was going to duplicate those 2 edges, so I just did. And continue. How about over here, up there, over here, and back around. This is the kind of thing that it probably looks easy when I'm doing it. You definitely want to practice this on these other examples on the paper. There you go. I think this is a minimum duplication circuit. I used every edge, and I duplicated only the edges which I said I was going to duplicate in that first picture there. All right. You can see my 4 duplications. I might ask you to specifically indicate where are you duplicating the edges. It would be here, 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 and here. Those are my 4 edge duplications. Right? Any thoughts about that one? This is minimum duplication circuit. This is maybe one of the more complicated types of things of this nature that you're going to encounter on the test. You definitely want to refresh your memory if you don't remember that so well. All right. What about minimum duplication paths? Let's try that. So here's my original picture again. Let's try a min-dup path. The difference between circuit and path is, in a path you don't have to start and end at the same point. What that means, the effect of that is when I do my business about trying to turn the odds into evens, I'm going to do the same thing, only those are all the numbers, those are all the degrees. I'm going to do the same thing about trying to duplicate edges to turn all the odds into evens, but I can leave 2 of them as odds and turn the rest into evens. That's the difference. With a minimum duplication path, you can leave 2 of them as odd. In fact, you must leave 2 of them as odd and make the rest even. And so actually, in this case, I'm going to decide to leave these 2 3s as odds because those were kind of especially inconvenient to connect them up. The other ones you can just connect with single edges. So I'm going to duplicate this edge and also this edge, right? So for this one, maybe I'll just write down, you need to duplicate edges until we have 2 odds, right? Whereas for a minimum duplication circuit, you have to duplicate edges until everything is even. In this case, we want to duplicate the edges until you only have 2 odds left. The others have become even. All right. And then, if you recall, those 2 odds, you're going to start and end at the odds. So I'll just choose one of them to be my starting point, and if you do it correctly, sort of automatically, magically, the other one will end up being your finishing point. So I'm going to start at this one, let's say, and I will, if everything goes well, I will automatically end up at the other one. And I'm going to do the same strategy about try to trace over these things without making any bridges. I'll do a separate picture. So I'll start down here. Let's see how I do. Come up here. Maybe I'll immediately duplicate that edge. That edge was going to get duplicated. And then also this diagonal was going to get duplicated. Most of the time when I've been doing these, I've been just sort of going immediately back and forth along the duplicated edges. You don't have to do it that way, but it usually works out okay. All right, I think that will do it for the minimum duplication path. All right, I covered every edge. Like I said, this is not the only way to do it. I was more or less making it up as I go along. It's just in the back of your mind, you have to make sure, like I said, to keep the unused edges all together. Don't split them up into 2 separate areas. All right, any questions about that? You should definitely practice this on the other pictures on the paper, just because it looks a lot easier when you watch me do it. Because I'm so graceful in my movements. All right? That's what they say about me. On the class evaluation survey, one of the questions, is he graceful in his movements? Strongly agree. That's what you say. All right, what else? So that was minimum duplication path. Next is Hamilton circuit. Can we do a Hamilton circuit in this graph? I don't know how this is going to work out. Finding a Hamilton circuit is much more complicated than Euler circuits, where you just look at the degrees and that's basically it. To find a Hamilton circuit requires some fun and games sometimes. You have to think carefully about this. But the way I would start is by shading in any edges which meet a degree 2 vertex. In this case, there's only one such vertex, but I have to use these two edges. All right? And now as I'm looking at this, I decide that I don't really like this example for Hamilton circuits. I probably wouldn't give you this one on the test, just because after doing that, you basically don't have anything else to do. You would now look for, are there any edges which would make a subcircuit, and you would exclude them, or any edges which would make 3 meeting at a single vertex, and you would exclude them, but I don't see anything like that. You might try to just look at this and guess a Hamilton circuit. That would be scribbling in the edges so that it meets every vertex and makes a circuit without repeating any vertices. Actually, I think it is possible in this one, although you can't really get there by step-by-step reasoning, at least not in the way that we usually do. But in this case, so maybe I'll just say some commentary here. Try the degree 2 vertices. This is always where you should begin, by scribbling in edges which meet degree 2 vertices, and then exclude edges which make a subcircuit or make 3 meet. But none of that really helps out in this particular example. Anybody else feel like you can just invent a Hamilton circuit here? Yeah, can you describe?
If you go up.
Okay, from here?
Very right.
Yeah.
And then go down the diagonal.
Mm-hmm.
And then go up the diagonal.
Mm-hmm.
And then go to the left.
Mm-hmm.
And then if you go down the triangular part, I'm
Okay.
just gonna go the other way.
Yeah, there's several ways you could do it.
And then across the right,
Yeah, great.
and then down into the right.
Yeah, that'll do it. So that is a Hamilton circuit. Although in this particular example, you don't really get there by this type of reasoning, unfortunately. That's why, like I said, I would consider this kind of a bad example to put on the test. It's not especially hard, because you can guess the answer, but I would prefer to put one on that is not all about guessing, just because I'm not really into guessing like that. Any questions about that one? All right, and then the very last column on the big chart there is spanning tree. Okay, find a spanning tree. This is basically always easy because you can more or less, I would say you can guess the answer, although it's not really much of a guess. You just make something up and it will probably work. All you have to do is scribble in edges so that you meet up with every vertex and don't ever make a circuit. You can have 3 meeting one another. So you could say, imagine that these things are all like houses that you want to run wiring between them, or plumbing or something. You don't have to use all the edges. Something simple like this would work out. That's a pretty standard, approach. I was just making like a grid or something. Sometimes the graph might look a little weirder and you can't make a straight up grid like that, but that is a spanning tree. Just finding a spanning tree is always easy. You can always just kind of make it up as you go. The more interesting spanning tree questions are about finding like the minimum weight spanning tree. That's considerably more interesting to talk about. But if I just show you a graph and say draw a spanning tree, that's essentially always easy. Yeah?
Yeah, so I know I'm asking a repeated question, but
That's fine.
what is a spanning tree? Again, like how would I know to draw that and label it a spanning tree?
A spanning tree just means a choice of edges which meet all the vertices but have no loops. So that's one way to do it. There are many, many ways to do it. Like I'll just draw another one that this is going to look totally different, but it's just any collection of edges which actually meets every vertex. Maybe I'll do those guys and these guys. There you go. There's another spanning tree. A collection of edges which meets every vertex but has no loops. There are many, many spanning trees in this graph. And I think that's all the questions of that type. I hope that was satisfying. Any